A journey inside the core. How the operating system handles hardware behind the scenes. Welcome, tech enthusiasts. Today, we are embarking on a fascinating journey deep into the core of computing, the operating system kernel. Have you ever wondered what truly happens behind the scenes the exact millisecond you press a key on your keyboard, move your mouse, or launch a heavy application? Let's decode the invisible, high-speed ballet between software and raw silicon. 1. The abstraction barrier, bridging silicon and code. At the lowest level hardware components, such as the CPU, RAM, GPU, and storage controllers, speak the language of electrical signals, voltage fluctuations, and binary pulses. An application cannot directly talk to these components without risking system crashes or security vulnerabilities. The operating system kernel acts as the ultimate master conductor. Through architectural layers like the hardware abstraction layer HAL, it shields software from the brutal complexities of raw hardware, presenting a unified, elegant interface for developers and users alike. 2. The symphony of interrupts, IRQs, and ISRs. How does the CPU know when a hardware component needs its attention? Instead of constantly checking or polling every device, which would waste massive amounts of processing power, the system relies on an event-driven mechanism called interrupt requests, IRQs. The trigger: when you press a key, the keyboard controller sends an electrical pulse down an IRQ line to the system's interrupt controller. The pause: the CPU instantly suspends its current execution thread, saves its exact state, registers, and program counter to the stack, and jumps to a specific memory address containing an interrupt service routine, ISR. The handshake: the kernel quickly acknowledges the interrupt, reads the data packet, e.g., the ASCII code of the press key, places it into an input buffer for the active window, and resumes its previous task, all in a matter of microseconds. 3. Device drivers, the universal translators. Since the core kernel cannot possibly know the intimate internal architecture of every single GPU, sound card, or network adapter ever manufactured, it outsources this communication to device drivers. Kernel space versus user space. Drivers often run directly in kernel space for maximum performance and hardware access, though modern architectures safely sandbox some drivers in user space to prevent system-wide crashes. Translation: the driver acts as a specialized translator, converting high-level, generic OS commands like render this 3D polygon or transmit this packet into the precise low-level instruction set required by that specific hardware model. 4. Direct memory access, DMA, and high-speed data flow. When transferring massive amounts of data, such as reading a 4K video file from an NVMe SSD into system memory, having the CPU manually manage every single byte would choke system performance. To solve this, modern systems use direct memory access, DMA. A dedicated DMA controller takes over the heavy lifting of moving data directly between the hardware device and the system RAM. The CPU simply issues a command with the source and destination addresses, then walks away to execute other processes, only receiving a final hardware interrupt when the entire data block transfer is complete. Epilogue: understanding these microscopic mechanics reveals the sheer brilliance of modern operating systems, orchestrating billions of transactions every second with absolute precision, stability, and speed. If you enjoyed this deep architectural dive into the world of technology, make sure to show your support. Like this video, subscribe to the channel Still Video, and hit the notification bell so you never miss another exciting journey into the heart of tech. Thank you for watching, and stay curious.